Good day everyone, my name is Li Zheshen and I'll be presenting my final year project titled Optimization of Environmentally Friendly Surface Treated Aluminium 7 Series for Aerospace Applications, developed via plasma electrolytic oxidation. Aluminium 7075 is widely used in aerospace applications due to its high strength-to-weight ratio and fatigue resistance. However, it suffers from severe corrosion, especially in chloride-rich aerospace environments. Conventional surface treatments like anodizing often fail to provide an ideal balance between corrosion protection, mechanical strength, and especially sustainability, as it relies heavily on hazardous electrolytes such as sulfuric acid and chromic acid. So, this project explores plasma electrolytic oxidation, or PEO, which is a surface modification technique that creates ceramic oxide coatings to improve corrosion resistance and hardness. Instead of using hazardous electrolytes, I employed citric acid and sodium bicarbonate, which are more eco-friendly alternatives. The three research objectives included, firstly, to investigate the feasibility of using eco-friendly electrolytes in fabricating nanoporous alumina, and secondly, to assess PEO coatings hardness, surface morphology, and corrosion-resistant qualities. Thirdly, I aim to optimize PEO process parameters via Taguchi method, and secondly via multi-objective particle swarm optimization, or MOPSO for short. So moving on to the methodology section, it was split into three main phases. The first one being the coding process, followed by sample characterization, and multiple objective particle swarm optimization being the last phase. For the coding process, let me briefly explain the coding setup, where a custom designed PEO DC setup was assembled. This included a high voltage DC power supply, a cooling bath filled with water and equipped with an oxygen pump to enhance heat dissipation, and a stainless steel container acting as the cathode. The aluminium 7075 samples in this case acted as the anodes, and the Taguchi design of experiments were used to systematically reduce the number of trials needed, where a total of 9 trials were needed, with varying voltages ranging from 300 to 400 volts. For current density, it ranged from 0.5 to 1.5 amperes per centimeter squared, and for sodium bicarbonate concentration from 0.1 to 0.4 molarity. Once the initial experimental trials in the Taguchi array were completed, I moved on to the second phase of the methodology, which was sample characterization. In this stage, 3 main types of characterizations were carried out. Firstly, VSAM imaging was performed at 3,000 to 20,000 times of different magnifications to observe surface morphology and, most importantly, to identify the presence of uniform nanoporous features which were ideal for this type of coating. Secondly, hardness testing was done via the nano-indentation method instead of micro-hardness, as micro-hardness testing is unsuitable for the thin nanoporous coatings produced via PEO in this study, as it typically requires thicker surfaces, so micro-hardness testers in this case may penetrate beyond the coating into the substrate, leading to inaccurate measurements. So the nano-indentation tests were done with the help of the company Anton Par, where I actually went to their site located at Shah Alam to carry out the testing. This testing measured the elastic modulus of each coating to give us an idea of how the coating reacts to deformation. Thirdly, the third surface characterization step was electrochemical corrosion tests, where again 3 different electrochemical tests were carried out on each of the 9 samples, namely open circuit potential, or OCP, electrochemical impedance spectroscopy, or EIS, and linear sweep voltammetry, LSV. These 3 tests were conducted in 3.5 weight % sodium chloride solution to mimic the real-world aerospace corrosive conditions. The tests were completed using a PalmSense4 device, and the data was analyzed via the PS-Trace 5 software. TEFL plots were generated to derive I-core and E-core values, which can give us a picture of the corrosion resistance for the 9 different samples. So the third and last phase of my methodology was to input the resulting hardness and corrosion data into the MOPSO algorithm, and the algorithm design was done in MATLAB version R2025A. The goal of this phase was to obtain a Pareto front, which identifies optimal PEO parameter settings that balances the trade-offs between coating hardness and corrosion resistance. And I will explain the outcome of this stage in detail in the results section. Here we can see the MOPSO convergence plot, which shows us all the dominated and non-dominated solutions obtained during the particle swarm within the search space that was set. So as we move on to the next section, here we have the results and discussion. Firstly, we start with the surface characterization of FYP imaging. For the FYP imaging analysis, only the best and worst coatings are shown here due to limited space. So samples 2 and 6, as shown here, they were categorized as best as they exhibited uniform nanoporous structures with well-defined pore boundaries, which indicated effective plasma discharge and stable oxide growth. So these correspond to better coating integrity and higher surface quality. Hence, this also confirmed the feasibility of using eco-friendly electrolytes for forming PO nanoporous alumina coatings, which was the first objective of this research. In contrast, samples 4 and 9 were considered the worst, as they showed non-uniform or defective morphologies, suggesting unstable spark behavior, overheating, or insufficient oxide formation. Moving on to the nano indentation results, again, the goal here was to evaluate elastic modulus of the coatings. The ideal values were found in samples 2 and 6, with elastic modulus of 69 megapascals and 65 megapascals respectively. It is worth noting here that although sample 4 recorded the highest value of 97.3 megapascals, this was deemed invalid because FYP analysis showed us coating failure for sample 4, meaning the indenter likely reached the substrate, which led to abnormally high elastic modulus values. These hardness trends correlate well with the FYP findings, where denser and more uniform morphologies yielded higher hardness values. Electrochemical testing was performed in 3.5 weight% sodium chloride solution using a 3-electrode setup. TEFL plot analysis revealed that samples 2 and 6 once again had the lowest corrosion current densities, I-core, as well as corrosion potentials, E-core, once again confirming high corrosion resistance among 9 samples. This again correlates with the FYP and hardness results, reinforcing the conclusion that samples 2 and 6 were the best performing coatings. Next, all the experimental data, no matter ideal or non-ideal, were fed into the MOPSO algorithm for carrying out the last phase of optimization. The two objective functions here in the algorithm were to maximize hardness and minimize corrosion rate. Using regression models that were built from the Taguchi experimental data, MOPSO produced a Pareto front, which is shown here, and this figure showcased the trade-off relationship between the two objectives. The optimization revealed that increasing hardness, indeed, as expected, often leads to higher corrosion rates and vice versa. So, from the 3D parameter space, the optimal trade-off was found at 390 to 395 volts for voltage, and for current 0.85 to 1 ampere per centimeter square, and 0.3 to 0.35 molarity for sodium bicarbonate concentration. These settings combined provide balanced coating with good hardness and acceptable corrosion resistance. So, depending on the application requirements, one can select the desired PO coating corrosion resistance or hardness and fine-tune the coating process parameters based on the obtained parameters in the 3D parameter space that correspond to that specific desired coating point in the Pareto front. In conclusion, this project has achieved all 3 research objectives. Firstly, the feasibility of employing eco-friendly electrolytes to form nanoporous PEO alumina coatings was confirmed. Secondly, coatings were successfully characterized using FYP, nano indentation and corrosion testing. And last but not least, the PEO parameters were optimized using MOPSO and Taguchi methods, identifying optimal processing windows. This research contributes to sustainable surface engineering by combining green chemistry with computational optimization to design high-performance coatings for aerospace applications. I would also like to take a moment to acknowledge my supervisor, Prof. Bushra, Dr. Mahmood, Anton Parr, and staff from CAREF and Surface Engineering Labs, as well as the Mechanical Engineering Department FYP Fund for making my project a smooth and successful one. Thank you very much.